Our next keynote speaker, Professor Paul Kwiat, the John Bardeen Chair in Physics and Electrical Engineering from University of Illinois Urbana-Champaign. Paul is an old friend and colleague from our time, 25 years ago now, at Los Alamos. He's as brilliant now as he was then. He's always pushing the limit and coming up with the next latest and greatest application of quantum entanglement. So I'll read you his official bio in a second, but I can't help but give you the more personal tidbits first. Like that he created and leads a really cool science-based escape room called Lab Escape. You can Google it or read about it in the New York Times, and hopefully he won't lock us in the room and make us solve physics puzzles to get out. Also, if you're one of his friends, you get his annual holiday cards, and they always arrive with this complex puzzle that you have to solve, like the one where you had to figure out that you have to put it in the freezer for 10 minutes so the invisible ink will appear and show you his holiday message. So this is all part of his creativity and wanting to share the beauty in physics with everyone. So hopefully he'll do that with us today. I'm glad he accepted this invitation because I've been wanting to get the quantum networking and timing communities together to help them and us understand their timing needs. So please look him up at lunches and coffee breaks and come to the quantum networking session tomorrow afternoon and talk to those folks as well. I think this is a great opportunity for our two communities to be together. So with that, I introduce Paul Kwiat from University of Illinois Urbana-Champaign. He's the inaugural director of the Illinois Quantum Information Science and Technology Center, IQUIST. He's a fellow of the American Physical Society and the Optical Society of America. He's given invited talks at numerous national and international conferences and has authored over 160 articles on various topics in quantum optics and quantum information, including several review articles. His research focuses on optical implementations of quantum information protocols, particularly using entangled and hyperentangled photons from parametric down conversion. He received the Optical Society of America 2009 R.W. Wood Prize as the primary inventor of the world's first sources of polarization-entangled photons from down conversion, which have been used for quantum cryptography, dense coding, quantum teleportation, quantum metrology, and realizing optical quantum gates. He's also done pioneering work on all-optical quantum memories and quantum-enhanced sensing. Professor Kwiat received his BS in physics from MIT in 1987 and his PhD in physics from University of California at Berkeley, 1993. Please welcome Paul Kwiat.
Thank you. Thanks so much, Daphna, and thanks for the invitation. She was very persistent in my not responding to emails, and I'm grateful for that because I agree entirely that there's a lot I think that our communities can learn from each other. Mostly we're hoping that you can solve all of our synchronization problems, although we might indicate that there's some tricks that we can put in to sort of help that might be useful as well. So I have a habit of always changing my talk titles just a little bit. So this is actually going to be about time and space. I have a pretty robust research group, and some of the students have been pretty helpful in helping me prepare for this particular presentation. But we are always looking for new collaborators and students and such. So please stay in touch. I'm really looking forward to interacting with people over the course of this workshop. So Daphna invited me to this conference, and I kind of accepted just because I know Daphna, without really realizing what I was getting myself into. So the thing is that I don't actually do precision timing and navigation, at least in the way that you do. And so in some sense, I feel like totally out of my element because I have a firm belief that almost everyone in the audience would be better at giving this talk than I would. But hopefully I can at least introduce you to some things that maybe you haven't heard of, and maybe those will be useful at some point. So this is the plan for the day. I'll give, it's kind of a trilogy in 4 parts, just an introduction, to some of the quantum concepts that we'll be using, and then why quantum, in particular quantum information science, needs clock synchronization, and then maybe why clock synchronization could be advanced by some of the quantum tricks that we have, and then that will, I think, bring us close to our close. Okay, so this is going to be an introduction of basic quantum-y things. It's hard for me to really know what this audience is. At the moment, I'm teaching a mostly sophomore and freshman course on electricity and magnetism, so I know what those people know, which is almost nothing. And I know what they think they know, which is almost everything. But so if some of this will certainly be repetitious of what was in the tutorial yesterday, the excellent tutorial that was given. Some of it is different. So anyway, hopefully, please, if you have questions, I would just say, just raise your hand, because I know for myself, if I get lost at the beginning of a talk, then it's really hard to follow everything else. So I'm happy to, as I tell my students, the sad part is that if I pick a random person of you, on average, you are average, which means that if you don't understand something, it probably means that other people don't understand either. Okay, so we're going to start at the very beginning with Albert Einstein. Always good to start with Einstein, who basically started quantum mechanics, as I'm sure you all know, basically by solving the mystery of the photoelectric effect by proposing that light was quantized. He didn't call them photons, but anyway, that's basically what they were, and he eventually got the Nobel Prize for that. And just to remind you all, right, the photoelectric effect, I have light that's impinging on a material, usually a metal, and then electrons will come off. And there are some sort of key features of this. One is that electrons are only going to come off if the energy of the light, I should say the color of the light, is high enough. If the energy of the photons given by Planck's constant times the frequency is high enough, otherwise you don't get any electrons coming off. And in contrast with sort of a classical description where the intensity of the light would make a difference, well, if the frequencies are too low, then it doesn't matter how bright the light is, you don't get any electrons off. And then above that threshold frequency, as you increase the intensity, you get more and more photons, so more and more electrons. The thing that is kind of most relevant for us right here is this notion of how long it takes the electrons to come off. And the point is that you can get the electrons to be emitted immediately. And that's a little bit strange, because you could, for example, have a dim light that's so dim that it would take you a week to accumulate the, 2 electron volts it needs to liberate that electron. And yet you can get the electron off in a microsecond or something like that, way before you've had enough time to accumulate that much energy. That's, of course, because the energy is coming at random intervals in photons. So we can ask the question, what does it mean? What does right away mean? How soon do the electrons actually come off? And I just Googled this as I was preparing for this talk, and this is the most recent result I could find, where researchers have been able to set the limit as low as around 100 attoseconds. And just to put that in perspective, 100 attoseconds, of course, is a tenth of a femtosecond, and 1 femtosecond is about half a period of light at 630 nanometers. So that's a very, very, very short time that the electrons come off. In response to light hitting the material, we could think then that this is then going to be the ultimate limit for what detector resolution times could be. So because I'm going to need them, I'm going to kind of do a review of that in one slide. So I'm just picking 3 sort of standard single photon detectors, photomultiplier tubes, where I have a photon comes in by the photoelectric effect, creates an electron that's accelerated to this dynode structure, where every time it hits another one of these dinodes, it creates more and more electrons, and then they're all accelerated. And these often have a jitter of something like a nanosecond. It's dominated by this cascade process. If we instead look at a semiconductor device like an avalanche photodiode, the photon comes in, excites an electron hole pair, which then has to migrate through this absorption region till finally gets to the multiplication region, and then we have this avalanche effect. And there the jitter is mostly determined by where this process actually takes place. You can have a thin device and you'll get a much better jitter, although you're much less likely to absorb the photon, so then the efficiency tends to go down. And then as a totally different type of detector, we have these superconducting detectors, so-called superconducting nanowire detectors. And those work by having a thin superconducting wire, and when a photon comes in and it's absorbed, it heats that wire enough that you break the superconductivity, and So the jitter there tends to come from where you actually land in this meander structure. And typically, if you go by one of these, they might have a resolution, a jitter of about 75 picoseconds. If you have friends at JPL, you can get them to have jitters of maybe only 15 picoseconds. Recent experiments where they just had a single short segment showed jitter down at the 3 picosecond level. OK, we're going to see soon that that's actually not enough for some of the things that we want to do. OK, next up, quantum light source. So a lot of my career has been spent studying spontaneous parametric down conversion. This is a process where we have a nonlinear crystal, and I have a high-energy pump photon, which occasionally will split into 2 daughter photons. Not very often, maybe only 1 out of 10 to the 10 times. And we have to satisfy momentum conservation for those 2 daughter photons, and also energy conservation. So the sum of them has to, sum of the energies of the 2 has to match the energy of the pump. So this is certainly not a new process. Any of you have seen a green laser pointer? Exactly that process is happening in reverse, where they take 2 infrared photons, add them together, and get green photons. So in fact, this was studied, one of the first experiments was to look at the timing nature of this was done in 1970 by Burnham and Weinberg, where again, they produced this pair of photons, and then using photomultiplier tubes, they looked at what the correlations, the time correlations were. And one could ask, well, what's limiting that time correlation in this data? And if this were one of my classes, then you'd have to pull your eye clicker and you'd have to indicate which of these 3 you thought was the right answer. And, but we won't do that here. So one option is the detector resolution. The second maybe has something to do with how long the pump pulse going through is, or what's the propagation time through the crystal that's creating the photons. It turns out in this experiment, it was absolutely the detector resolution. Those are pretty slow detectors back then. So fast forward about 15 years, and the group of Leonard Mandel, who's like one of the godfathers of this field, did a much more precise measurement of the time delays in this experiment. And they did it with a crystal whose the propagation time through that was about 400 picoseconds. And they did it with 2 different types of pumps. One was a 40 nanosecond pulse, and the other one is 670 picosecond pulse. But the actual data for these correlations were more like 160 picoseconds, so not governed by either of those 2 things. And they say that the results are consistent with theoretical predictions in the sense that at the moment they're still limited by their detectors. The theoretical prediction is that the correlation time should basically be dependent on the bandwidth of the photons. So it should go like 1 over the bandwidth. This is a formula for the coherence time of any optical pulse that has a bandwidth of delta lambda. And if we just put in 800 nanometers for the wavelength and 10 nanometers for the bandwidth, like they had in their experiment, then you get something like 160 femtoseconds. OK, so now that's starting to be a pretty short time. And now if you're a student in Len Mandel's group, you say, what the hell, I'm screwed because my detectors are 1,000 times slower than that. How will I ever possibly measure something that's only 160 femtoseconds? OK, so now I get to teach you one of the most basic and important quantum effects in quantum optics. This is the so-called Hong-O-Mandel interference. So 2 of Mandel's other students, Hong and O. So I'm going to take 2 photons and I'm going to impinge them on opposite sides of a beam splitter, a 50-50 beam splitter. And obviously each photon can be transmitted or reflected. So there are 4 different things that can happen, as shown here. It turns out, and if the photons are distinguishable from each other, then all 4 of those things happen, and they each happen with a 25% probability. But if the photons are indistinguishable from each other, then it turns out that these 2 central possibilities, the 2 ways that you could get a coincidence count between the 2 output ports, will destructively interfere. And the reason that happens is that there's this I phase shift, or a 90-degree phase shift, when you bounce off a symmetric beam splitter. And so if you calculate the probability amplitude for this process where both photons are transmitted, and the one for this where they're both reflected, they have the same magnitude, but this has a factor of I squared, which is to say -1 relative to this. So when you combine them, they completely cancel, and the 2 photons stick together, and they both go off the same side. So in a typical experiment, we might change the delay of one of the photons coming to the beam splitter relative to the other one, and if they arrive separately, then we will get coincidences. But if they arrive at the same time, then we'll see the suppression in the coincidences, so-called Hong-O-Mandel dip. And the width of this dip is going to depend on the photon bandwidth. So the bigger the bandwidth, the narrower the dip. I'll just say one of the things that's nice about this sort of interference compared to classical interference like a normal Mach-Zehnder or Michelson interferometer, first of all, it's immune to unbalanced loss. So if you put a lot of loss in this one arm, if this were a classical interferometer, the fringe visibility would go away. But in this case, if I put a lot of loss in this arm, the two interfering processes of both photons being transmitted and both photons being reflected, they both have the same loss. So both the amplitudes are suppressed by the same amount. So you still have complete interference. It turns out this process is also immune to odd orders of dispersion, which is helpful for some things. And because it's a two-photon process, it's also much robust against background. OK, so reasons why you might want this. OK, so this was the experiment that Hong-O-Mandel did. And they saw this dip that had a width of about 100 femtoseconds. Or they changed the position of the beam splitter, and that corresponded to a wave packet width of about 100 femtoseconds. And they indicated that you could probably then determine that the width to better than a femtosecond, and the location of that to better than a femtosecond. And in fact, this was sort of my introduction to this. When I was a graduate student, I worked with partner Ephraim Steinberg, and we did an experiment looking at the photon tunneling time using this Hong-O-Mandel dip. And in fact, we were able to get a resolution of 0.2 femtoseconds, so 200 attoseconds. So now we're actually starting to get to the point where one can start to look at interesting things that you just wouldn't be able to do any other way. OK, I'm going to ratchet it up now to something that's much more current, which is we're going to sophisticate or add a new feature to this Hong-O-Mandel measurement by adding frequency entanglement to the input. So I'm going to have two photons, just as we did before, but they're going to be frequency entangled. What that means is that one of the photons, for example, is red, and the other one is blue, but you don't know which is which. It's a quantum superposition of having the red one in mode A and the blue one in mode B, and vice versa. And it turns out if you work out the theory of this, it's not that difficult to do, you still get a Hong-O-Mandel dip that we had before, but it gets modulated by the beat note between those two frequencies. OK, so what does that mean? So if the two frequencies are the same, then you just get the normal dip. But as I pull the two frequencies apart, so I'm showing here in wavelength going from 800 nanometers out to 1,550 nanometers, I populate this dip with these fringes, and the fringes get narrower and narrower, or more and more closely spaced, as the two frequencies become larger and larger. OK, so that's going to be nice, because that's going to give us an even much better resolution than we would normally have just with the Hong-O-Mandel dip, because it's hard to get a very sharp dip without having a very broad bandwidth. It's not that easy to make, and it's also hard to have optics. For example, an optical system that would work well from 800 nanometers to 1,600 nanometers, that's actually quite difficult to make. On the other hand, an optical system that works well at 800 and 1,600 but doesn't have to work all the things in between, that's actually relatively easy to make. OK, so we've set something like that up in our laboratory where we can create these non-degenerate, meaning they have different energies, non-degenerate photons. And we send one photon through basically an empty path, and the other one goes through a path where we can change the path length. And then we detect the photons on the end using these superconducting nanowire detectors. I should say, although these do have the fastest jitter of all the detectors I showed you, it's completely irrelevant for the Hong-O-Mandel dip. Because the Hong-O-Mandel dip, we're measuring something that has, with a time resolution of, 10 femtoseconds or 1 femtosecond. The detectors are still way, 1,000 times or 10,000 times slower than that. So you can have very slow detectors and still get very good time resolution using this sort of technique. OK, so this is just some data showing these fringes that we expect inside of this Hong-O-Mandel dip. And I'm also plotting in this bottom curve the Fisher information. That's a way of characterizing how much information you could extract about the actual relative time of the two photons coming in, for example. And not surprisingly, if you want to figure out the timing well, you want to sit on a steep edge. If instead that's where the Fisher information is maximum, if you sit in a case where the fringes are flat and rolling over, then there's no Fisher information. OK, in any event, with our current experiment, after collecting about 250,000 photon pairs, which takes about 5 seconds, we can now measure with a resolution of about 2 attoseconds, or 0.7 nanometers. So that's pretty good. There was another experiment that used a conventional Hongo-Mandel without these extra fringes, and they were also able to get similar kind of resolution, but they had to count for basically 10 hours in order to get that, and not for 5 seconds. Okay, so we'll come back to this way at the end. I'm going to go back to the original Hongo-Mandel experiment, which is just this. I have a source, 2 photons that are coming onto the beam splitter, and the state of the light after that beam splitter is one where I have 2 photons in one mode and none in the other mode. So 2 photons in the upper path and none in the bottom path, or 2 photons in the bottom path and none in the upper path. And then I'm going to combine those in another interferometer, and I'm going to ask, well, what will I see as I change the path length here? So the phase that you pick up is just the normal phase that you would get for one photon going through this, let's say, relative path length change, a 2 pi d over lambda. But then I have to multiply by 2 because both photons are getting that phase. So you get to multiply the phase shift that's acquired by this 2-photon state by a factor of 2. And then I've also written this in terms of frequency and in terms of the energy of the photon divided by Planck's constant times the time. Okay, so let's just show the data. The top curves are what you get if you block one of the inputs so that I only have one photon that's going into this interferometer, and I see fringes, and the fringes are at the wavelength of the light. So the fringes are at 800 nanometers, which is the wavelength of each of these 2 photons independently. But when I look in coincidence, when I have both paths open, so I'm actually seeing this sort of overall state that's going in, now I get fringes that are at twice the frequency, or twice the oscillation period, if you will. Well, twice the frequency, half the period. So that's better if you're trying to do metrology, to have things with twice the oscillation frequency. So one of the reasons I wanted to show this is to now make a jump, sort of a conceptual jump, to doing the same thing with atoms for making better clocks. So this was a paper by Dave Wineland, who is one of the world leading ion trappers. He got the Nobel Prize for trapping ions quite a while ago. And they realized that if you could do the same sort of trick with atoms that I just did with photons, you could get an enhancement for clocks. So here's the thing. I've got this, an atom, a 2-level atom, has a ground and excited state. They have an energy difference E. And so if I take the atom and I start it in the ground state and I excite it into this superposition of ground and excited state, it will then evolve with this phase, this time-dependent phase, sort of like a clock. And that's basically how you make, and obviously all you clock people know this much better than I do. So if instead you can have an entangled set of atoms or ions where they're either all in the ground state or they're all in the excited state in this quantum superposition, and you do the same sort of transition, then you get the same sort of oscillation, but again, you get to multiply by the number of atoms, just like we got to multiply by the number of photons before. So now your clock is effectively going at n times the rate, and having a faster clock obviously allows you to make better measurements of time or frequency in this case. And so the clock is going at n times the rate. On the other hand, you've had to use up n of your atoms to get that, as opposed to treating them all n independently. So because you have n fewer systems, that's going to reduce your statistics by a square root of n. But you get a factor of n enhancement because things are oscillating n times as fast. So overall, you have a net square root of n improvement over this so-called shot noise limit, or standard quantum limit. And when you, so normally you would have a resolution in frequency that would go like 1 over the square root of n, and using this trick, you can get it to be 1 over n. And so people are definitely working toward trying to do that. One thing is that it's not that easy to entangle lots and lots of atoms and ions. So I guess I don't know what the current record for that is. I don't know, maybe 10 or maybe 30 or something, but not like 10 to the 6. I guess people don't quite know how to do that yet. Okay, so that may be another case where quantum could be helpful with clocks and such. Okay, so we're going to change topics a little bit. It seemed appropriate when we're talking about photons sticking together and crashing into each other at the beam splitter. Okay, so That was sort of my intro. Now I'm going to start talking about why, in particular, quantum information processing needs clock synchronization. So I need to give a little introduction to what is quantum information. It's obviously a big field, not such a new field anymore. Encompasses many things like quantum computing, quantum communication, metrology, with a lot of very interesting fundamental science underlying it. The main entity that we often talk about are the quantum bits, which are the analog of classical bits. Classical bits, of course, classical information we typically encode using binary digits or bits, zeros or ones. Key factor of those, of course, is that they're copyable, as evidenced by the fact that you are all seeing the word copyable at the moment. On the other hand, quantum bits, they can certainly be in a state zero, a state that we would label 0, a state that we would label 1, but they can also be in my state had a run over to the next line. They can also be in an arbitrary superposition of a 0 and a 1. And one key feature is that you cannot copy unknown quantum states. So there's lots of different ways that you could implement these depending on what physical platform you have. So for example, you could say that the 0 state was the ground state of an atom and the 1 was the excited state, or it could be this 2 spin states of a spin-a-half particle, or it could be 2 polarization states. They're all mathematically equivalent. Some are better than others depending on what you're trying to do. And we represent this quantum information as residing on the surface of a sphere called the Bloch sphere. I had a secretary who said we were just trying to confuse her by calling it a Bloch sphere because it seems like a block and a sphere are exactly the opposite. But it's, anyway, B-L-O-C-H. Right, so this is the way that you could represent something that has an arbitrary, this is an arbitrary qubit written here, where I've got these two variables, theta and phi. Theta is the polar angle, and then phi is the azimuthal angle here. So it's like describing with a longitude and a latitude. You can kind of get a sense why quantum information is going to be markedly different than classical information, both because the states are living in this a space, actually, on a sphere. But the other thing, if we think about gates, if you have a classical bit, there's only one, maybe 2 gates. I guess there's 2 gates you can do to a classical bit, right? You can flip it, or you can leave it alone, a rather uninteresting gate. In the quantum case, we can take this Bloch sphere and we can rotate it about any axis by any angle. So there's an infinite number of single qubit gates you can do. Turns out you don't need to be able to do an infinite one. You need to be able to do just a couple, and then you can fabricate, or you can create out of assembling of just a few, you can create any set of them. But in principle, there's an infinite number. So there are, for example, some gates that classically would be nonsensical or impossible. I'm just going to just describe one of them, the so-called square root of naught gate. So that's shown here, where I'm going to drive my system from a 0 to the superposition state. That's the square root of naught, because if I apply that same operation again, it will take me down to the 1 state. Or if I started in the 1 state and I applied it, it would take me from 1 out to here. And then if that's, again, square root of naught. And then if I applied it again, it would take me up to a 0. So you have to apply it twice to get a NOT gate, which, of course, classically doesn't happen. We'll come back to this as an example later on. As a 2-qubit example, and to start understanding why this is maybe more powerful, I could have this is called a controlled NOT gate. This is a gate whereby if the control bit is a 0, the target bit is going to stay whatever it is. And if the control bit is a 1, the target bit is going to flip. So that's also like a exclusive OR in classic gates. But the difference is that in this case, I could make my control bit in a quantum superposition of being a 0 and a 1 at the same time. And then what happens is that, well, the output is a superposition of the control bit having been a 0 and the target bit having not been flipped. Let's say it started with a 0, and the control bit having been a 1 and the target bit flipping. And so this is an entangled state between these 2 bits. And we'll talk more about entangled states in just one slide. I just want to say one word on why quantum computing is a lot more powerful than classical computing. Again, if you know anything about quantum computing, you certainly are already aware of this. But we certainly know that we can simulate any classical computer on any classical computer. That's well known in computer science. If you have an n-bit n-bit classical processor, you need of order n bits to simulate that on another computer. It turns out you can simulate a quantum computer on a classical computer, but if you have an n-qubit quantum computer, you need of order 2 to the n bits. So let's say you had a 1,000-qubit quantum processor, which the world does not, but 10 years from now, the world will. That will require about 2 to the 1,000 classical bits to simulate. 2 to the 1,000, that's like 10 to the 300. That's a lot. That's an unimaginably lot. Because as far as we know, in the observable universe, there's only about 10 to the 80 particles. So you run out of electrons and protons in the entire universe before you come anywhere close to being able to simulate just a 1,000-qubit quantum processor. OK, so this is just a plug for why quantum computing might be useful and have a lot more power than classical computing. Let's talk a little bit about entanglement. And this is my favorite analogy. It's a simple one, but it will get some key ideas across. So imagine that Daphne and I each have coins, and we're going to flip our coins. And if they're assuming they're fair coins, I'm going to get heads half the time, tails half the time. Daphne is going to get heads half the time, tails half the time. So we'll have all 4 possible combinations. But if these are entangled coins, we could instead have a situation where whenever I get a heads, she'll get a heads. Whenever I get a tails, she'll get a tails. So they're always correlated. Completely random, but completely correlated. This is a thing that cannot exist classically. So as a consequence of this, I can know what result Daphne will get when she flips her coin, even if she's on the other side of the country, in our case, or the planet, or no matter how far apart we are, there'll be this, what Einstein called spooky action at a distance. Now, I just want to clarify something, because at this point, oftentimes people, not you guys, but then say, I can send signals very quickly through space, instantaneously. But I cannot, because I can't control what I get with my coin flip. I'm equally likely to get heads or tails. Therefore, I cannot control what Daphne gets. So there's no superluminal signaling possible here. We have shared remote randomness, and we can use that, for example, for quantum cryptography and other applications. But we can't send signals instantaneously. OK, so how do we make entanglement? So there's, and in particular, photon entanglement. So I'm going to go back to our spontaneous down conversion, parametric down conversion, where I have a high-energy photon that splits into 2 daughter photons. And I didn't say anything about the polarizations before, but now I will. So in this particular example, the 2 daughter photons, they're created on opposite sides of this cone. That's to conserve momentum. And they're both horizontally polarized. And that's if I had it turns out, a vertically polarized pump photon coming in. If I take this crystal and I send in a horizontally polarized pump photon, it turns out it doesn't do the splitting at all. It just goes right through. OK, if I take the entire system and I rotate it, so I'm going to rotate the crystal by 90 degrees, then, and now I'll pump with horizontally polarized light. Now I will get out a cone of vertically polarized photons. And the trick to getting entanglement is in something that's really stupid. I have a patent for this really stupid idea, but it's really obvious, I guess I would say, which is that you don't know whether or not the photons come from the first crystal and are both horizontally polarized or from the second crystal and are both vertically polarized. And so if you simply send in a superposition of horizontal and vertical in the pump, that gets mapped into this polarization-entangled state where neither photon has a definite polarization, and yet they always have to have the same polarization. So neither photon knows what its polarization is, but as soon as you measure the polarization of one of the photons, you'd know the polarization of the other. Maybe just to indicate why that might be helpful, let me pick a particular value of this phase. Let's say that the phase was 0, so this is vertical, vertical plus horizontal, horizontal. It turns out if you write that in any linear polarization basis, the 2 photons always have the same polarization. So if one of them were measured to be 13 degrees and you measured the other one in the 13 degree and 103 degree basis, you would also find that it was always 13 degrees, never 103 degrees, just to give you a sense of these kind of correlations. Now, you might think, well, OK, quantum mechanics doesn't tell you what those what the measurement result would be, but maybe the photons themselves somehow know. Quantum mechanics says that's not the case. Anyway, in 1965, there was a theorist, John Bell, who showed that, in fact, there are measurements you could do that would distinguish between the quantum mechanical statement that basically the photons don't have any definite information, it's only in this global quantum state, and this much more intuitive sense that the photons really do know what their polarization is, even if quantum mechanics doesn't specify it. That's kind of what Einstein wanted. Anyway, that's the test for that is so-called Bell inequalities. And I put this up just sort of out of historical content because last year, these three physicists, John Clauser, Alana Aspey, and Anton Zeilinger, got the Nobel Prize for using entangled photons for doing these tests of Bell inequalities and for basically kicking off, it says quantum information science, let's say quantum network science in particular, using these sorts of things. Okay, so one of the things that Anton Zeilinger did, he did one of the first experiments on quantum teleportation. So that's going to lead us into some other things, so I want to talk just a minute about that. So here's the scheme. I have some unknown quantum state, and I want, or rather Alice wants to get it to Bob, but for some reason she cannot send it directly. Rates are too high that time of day. There's just no open channel at the time. Anyway, she can't send it directly. But Alice and Bob share an entangled pair of particles, let's say photons. And Alice is going to make a particular measurement on these two photons that are coming to her, a so-called Bell state measurement. And she'll get one of 4 results. It's completely random which 4 results she gets. But anyway, one of 4 results. And she has to send some classical information to Bob. And he'll use that to do one of 4 transformations to his photon. And they're easy transformations, like rotate the polarization by 90 degrees, or put a pi phase shift on one of the polarizations, or do both of those things, or don't do anything. Actually, those are the 4 transformations. That's it. That's the whole story. So, OK, so. And if he does that correct transformation, and he knows what the correct transformation is because of this classical information from Alice, if he does that, then this initially, this quantum state over here with its, living in some random location on the Bloch sphere, suddenly Bob is holding that. It doesn't exist anymore over here. That would have entailed copying, which you can't do any copying or cloning. But anyway, we managed to get the state from over here to over here without sending it directly. So that's quantum teleportation. Now, the question is, what is this mysterious Bell state measurement that we talk about? That surely is going to be something extremely complicated and hard and impossible to understand. But no, it is in fact the same old thing we talked about. It's just the Hongo-Mandel. We just take the 2 photons and mix them on an ordinary beam splitter, and we just look at the 2 detectors. And if both detectors go click, that means that these 2 photons were in one particular quantum state. It turns out they were in a quantum state. Actually, I guess we could even, they're in a quantum state where the 2 photons always have perpendicular polarization. I can even justify why that would be the case. If they were in a state where they had the same polarization and they're both going to the beam splitter, well, then they're going to stick together, because that was the whole point about the Hongo-Mandel effect, is that 2 indistinguishable photons, when they get to the beam splitter, are going to go off the same direction. So it turns out if instead they have orthogonal polarizations, then they go off opposite directions. OK, so the Bell state measurement for teleportation is nothing more than the Hongo-Mandel result. OK, let's ratchet this up and make it even more interesting. What happens if the thing that I'm trying to teleport is itself part of an entangled state? So now I have 2 entangled sources here. They're each sending a photon to this middle Bell state measurement. And now, if I get a successful Bell state measurement on this, I've effectively teleported this photon, this central one, over here. And I've teleported this photon over here. So I had these 2 photons, this entangled pair, no connection initially. Then I measure these 2 guys to be entangled. Then they're gone. And then the 2 outer photons end up entangled with each other. So this is a way of linking together longer chains. And as you can imagine, then this entanglement swapping is sort of like the key element in what we would call a quantum repeater. You can't do, if you have a long link and you have loss in it, you can't do repeaters like you do in classically. Classically, you would like make a measurement of the signal and then regenerate it. As soon as you try and make a measurement of this quantum state, you've collapsed it, so that doesn't work. If you just try to amplify it, that's like copying, and I already said you can't do copying, so that doesn't work. So you have to do more sophisticated things like a quantum repeater here. But it's based on this phenomenon of entanglement swapping. So again, the Bell state measurement, in order for this to work, I have to do this Hongo-Mandel measurement. And that means the photons have to arrive simultaneously in order for this to work. OK, and now we need to understand, what do I mean by simultaneously? And I really care about this because if I want to do long links and I want to have a whole bunch of quantum repeaters to make my network going, I need to have this happen everywhere I have this repeater. So this is going to be a critical constraint for us. And this is just a OK, so this is the thing. I've got the two photons. I want to know how well do they have to match? Do they have to line up when they get to the beam splitter? And let's say that their separation is capital delta T, and their width, ignore that sigma there, and their width is capital T. And this is a calculation of the, if you do entanglement swapping using this method, how does the fidelity of the output, the fidelity of these two outer photons being entangled to each other, how does that vary depending on the relative pulse overlap, where I've plotted this as delta t over t. So when delta t is equal to 0, that means they're completely overlapping. When delta t is equal to t, that means they're kind of half overlapping. And we see that the fidelity drops pretty quickly. So basically, we're going to need to make sure that the photons arrive at that central beam splitter to within a fraction of their width. And that width might be something like a picosecond, or 100 femtoseconds, or 10 picoseconds, or something like that. So that gives you a sense of how well the synchronization needs to be. Probably, if we need to have very high fidelities, we need to have something like sub-picosecond synchronization. In a quantum network that we don't quite have yet, we have links on the ground. No one actually has quantum repeaters yet. That's what those are. Certainly, there's effort now trying to do things with satellites. My own group is working on some stuff with drones and going to moving vehicles. One trick, if we think about now trying to incorporate these other things like entanglement swapping and teleportation, very big challenge. How do you synchronize photons arriving at a beam splitter between sources that are in relative motion? So for example, this drone is flying along and relative to this truck that's going in some other direction, and I need the photons from each of them to meet at a beam splitter. They need to meet within a picosecond. Oh, I'll be generous, even a nanosecond. Not that easy when the thing is actually flying, or for example, when you have a satellite that's flying overhead at 7 kilometers a second. How do you solve that synchronization problem? And we know how to solve one specific case of that, but for the general case, I would say I don't have any idea, and I'd love to talk to people about what would be a good way to do that. OK. This is why would you want a quantum network? So I've already indicated that you could do secure communication or quantum cryptography. You might be able to make better measurements with quantum sensing. If you have a quantum network, you can remotely program a quantum computer, sort of like quantum cloud computing. But the example I want to talk about now is actually hooking together two quantum computers so that they can work together and act like one big quantum computer. And the reason for doing that, going back to this the power of a quantum computer over a classical computer, I said to simulate a quantum computer, you would need 2 to the n qubits. So if I have two separate quantum processors that are each 1,000 qubits, to simulate that would take 2 times 2 to the n, 2 times 2 to the 1,000. But if I can have them entangled with each other so it looks like one big quantum processor, then that's 2 to the 2,000. And 2 to the 2,000 is a lot bigger than 2 times 2 to the 1,000. It's about 2 to the 1,000 times bigger. So if you have two quantum processors and they act like one big one, they are more powerful than two independent quantum processors in exactly the same way the quantum processor, each one is more powerful than the classical processor to start with. But there's a problem. And this is why distributed quantum computing has pretty severe synchronization needs also. So this is a review article. I don't expect you to read all that. I'm just going to pull out the key segment here, which is saying that if we have a quantum superposition like we've had before, where I care about the relative phase between the two, the coherence that you have to preserve is not just the coherence within that qubit between the 0 and the 1 state, but also it's the coherence relative to the master clock that's driving the entire system. And so now I'm going to go back to my square root of naught gate. And let's say I'm going to do the first square root of naught in my one quantum processor, and then I'm going to teleport or transmit that qubit to the other quantum processor, and I'm going to finish it. That's the simplest distributed algorithm you could think about. I don't know why you would want to do that, but let's say you want to do that. So I start out with my superposition of ground and excited state, and then it's time evolving, as we've already shown before. And so that I put this now at the superposition in between the two, and we could think about this as just kind of whipping around at frequency omega. Whether or not what trajectory it takes depends on the time, the exact phase of when I drive whatever laser I'm shining onto my atom or whatever microwave system, microwave pulse. It's only going to go in the correct direction to finish this gate if it's applied with the correct phase. So that means that we have to have phase synchronization between the two quantum processors. Not just the quantum side, but all the other control circuitry, all the other lasers and microwave circuits that I'm driving on them. So that's a pretty serious requirement that is absolutely going to need help from you guys in order to have that be functional. I would say that many people are not aware of this, including people doing quantum computing. I discovered that because I wasn't sure about it. I thought it might be true, and I asked a lot of my friends, is this true? And a lot of them said, I don't actually know because we haven't been worrying about, we can't even get our local quantum computers to work, much less trying to hook them together yet. So people haven't been too worried. But in the long term, this is going to be a big issue. And if you're trying to do distributed quantum sensors, you probably have a similar kind of constraint. OK, we're going to change topics again. What might quantum have that would help in terms of clock synchronization? So we've already talked a little bit how quantum might help in terms of like getting better frequency standards, as an example, by making this superposition of n atoms in the ground state or n atoms in the excited state. I'm going to just limit myself to talking about clock synchronization. So this was one of the first protocols that I'm aware of actually being implemented, maybe one of the first ones that was proposed, I'm not sure. Anyway, by Antje Lamas and other people in Christian Kurtziefer's group. And so the protocol, you don't have to read all these details. This is actually obviously pretty recently. The protocol is shown here. So I'm going to have two down conversion sources. Source one, they're each going to produce two pairs. They're each going to produce one down conversion pair. And so one of the photons from source one is just going to be detected locally at this detector, and we're going to record when that happens. And the other photon is going to go over the channel between Alice and Bob, and then it's going to be detected at this other detector on Bob's side, who will record when that happens. Similarly, there's a source on Bob's side that's going to send out two photons. One of them is measured locally, and we record that timestamp. And then the other one is transmitted to Alice over the same channel, and then she'll record where it goes. And I'm not going to go through the details of this, except to say that when you look at the cross correlation, you find that if the propagation time going to the left and going to the right is the same, then if you look at the correlation, after Alice and Bob have their classical conversations about when their clocks were clicking, and you see these two correlation peaks, if you look at the midpoint of that, that will give you the clock offset between the two clocks. And they demonstrated this with fibers of several different lengths and showed that as you increase the acquisition time, the precision gets better. And in fact, they were able to get a precision down to something like 50 picoseconds after accumulating for 100 seconds at 200 counts a second. So after accumulating about 20,000 photons. So, OK, so that's a demonstration of using just the fact that the photons have these correlations with them. I talked quite a bit about the Hongo-Mandel effect. So the question is, can we use that to somehow get to have better clock transfer or as a technique? And there was this proposal by Tom Botter and I think it's William Golding a number of years ago, 20 years ago now. And so I'll talk through this. So I'm going to make a pair of photons. I'm going to send one off to station A, and it's going to have a mirror. For the moment, just pretend it's a mirror, or anyway, some of the photons will be reflected back. I'm going to send the other photon to station B. Some of the photons are going to be reflected back. And then we have a beam splitter here. We're going to look for a Hongo-Mandel dip. Now, as shown here, A is further away than B. So inside of this station, we're going to have a tunable delay. And we will adjust that delay until we're sitting at the bottom of this Hongo-Mandel dip. Now, once I've done that, I know that the distance, the effective distance from this central station to A and from the central station to B, taking into account this extra delay I put in, I know that those are the same. And that's kind of shown here in this time diagram where these are the photons that didn't go through the delay back to this beam splitter, and these are the photons that did go through the delay back to the beam splitter. They're arriving at the same time. So that's like the first half of the protocol. Or actually, in this case, it's steps 1 through 3. And then, because I did this with actually beam splitters, some of the photons are actually just going to go right through. And I'll just record when the clocks go click from those photons. I know that they're born at the same time, because that's the whole point of the Hongo-Mandel effect. And I also know that they propagated exactly the same time, basically, to get from the central station to either A or to B. So I can use that then to back out what the clock difference, what the offset between the two clocks is. OK, so that was demonstrated actually also quite recently. There was a couple groups in China who did a demonstration of that. So they have the pair source here, and they're going to send one photon this way, one photon this way. A couple things can happen. The photons could be, the photons are going to go out. They're going to go through some dispersion compensating fibers, so they don't have to deal with dispersion so much. And then there's a beam splitter, and either they could bounce off these Faraday reflectors. So this is basically, Faraday rotators. So this is basically the mirror that's going to bring the photon all the way back and then into this beam splitter. Same thing with the other photons. So we will go through a controllable delay line here that enables us to equalize the path length so that I have a Hongo-Mandel dip sitting right here. And then the other thing that could have happened, instead the photons could have gone to these detectors, and they're using these nanowire detectors to detect them. OK, so with this system, they were able to get something like a couple picosecond precision in the measurement of this time offset. I will say that this system is obviously going to be ultimately limited by the resolution time of the detector. So they have these nanowire detectors that have a resolution. I don't know, in their particular experiment, it was probably 50 picoseconds or something like that. And then because you collect multiple photons, you can beat down the jitter by 1 over the square root of n. But nevertheless, that is going to be the ultimate limit on how well you can do this sort of synchronization. OK, so the next thing is a way that you might be able to do better than that. This is an idea that I had when I was worried that I would have nothing to say when I came to this conference. So it is not vetted by any peers other than people who are closest enough to me to listen to it. So if there's something terribly wrong about this, I'd love to hear about it. So the idea is that, so the point is, I'm stuck with the fact that my photons have correlations of maybe 30 femtoseconds or a picosecond. But my detectors have resolution of maybe 10 picoseconds or 100 picoseconds if I don't want to use these superconducting detectors that I have to have cryogenics for. Maybe I don't want to fly those in my CubeSat. I don't know where you can fly them in a CubeSat. Impossible, at least today. So we can use a nonlinear process. In our field, this is called a quantum pulse gate, but it also works with a classical pulse. So here's the thing I'm trying to detect. I'm trying to detect when it's going to arrive. And I'm going to put that through a nonlinear crystal with another pulse. And as long as they don't arrive at the same time, and I'm basically going to upshift its energy. So this is, to say, 1 photon, for example, and this is lots of photons in this other pulse. And there's enough that if the 2 photons arrive at the same time, I'm going to take this, say, red photon, and I'm going to add it to, let's say this is a greenish photon, and I'm going to end up with a blue photon. And then I'll just detect that I have a blue photon, I don't need to have a fast detector. The point is I'm only going to get the detection. I only see a blue photon if the two photons arrive, if the two pulses arrive simultaneously at the crystal, simultaneously to within the width of the pulses. Now, okay, so that what I just said is absolutely true. Maybe not all that useful because I'm going to try and use this to try and equalize the paths, and I don't necessarily want to have to do a scan of these two pulses over each other. I'd really like to just get the timing information in one go without having to do a scan. And so what I can do is I can put a chirp, a frequency chirp, on this bright escort pulse. And now, when I add the two colors together, it's going to depend what those energies are, is going to depend where the thing I'm trying to time, the short one, is where that fell on this chirped pulse. Because depending on where it falls, it's seeing a different color, a different energy of the photon that it's being added to. And so that means that the photon that comes out, there'll be a correlation of when it came relative to this pulse and what frequency it has. Okay, so we can use that then. If I can measure what the color coming out is here, I can use that to infer what the position or what the timing of this was relative to the other pulse coming in. And the resolution that you get, it turns out, is governed by the group delay dispersion of this chirp pulse. And of course, the resolution of your spectrometer and the wavelength that you're using, and by this fairly simple formula. And if you put in, for example, that you had a resolution of 130 kilohertz on your spectrometer, and this fairly realizable 60 picoseconds per nanometer group delay dispersion and a wavelength of 800 nanometers, you get a time resolution of something like 20 attoseconds. So that's looking pretty good about being able to measure things, right? Okay, so I don't have data on this, but so that's the idea. Now, 130 kilohertz. I don't know if any of you do spectroscopy, but actually that's not so easy for a spectrometer to measure 130 kilohertz. And there is this other technique called quantum weak measurements. And this fellow that I did some work on a while ago, and anyway, this fellow John Howell, who was at Rochester then, came up with a way to make very precise frequency measurements. Basically, you send the light into an unbalanced interferometer, and you've got a prism in here, and depending on whether the light goes clockwise or counterclockwise, it gets deflected sort of to the left or to the right, and that disrupts the interference that you see on a detector over here. I don't want to go through the details of this other than to say they're able, with this, in their experiment, they were able to see a 130 kilohertz frequency shift. So that's why I put 130 kilohertz in the previous slide. Okay, so I'm actually down to my last slide, which is a protocol that combines all of these. I'm calling it my Homermobile protocol. I don't know if any of you are fans of The Simpsons, but there's an episode where he's invited to invent a car, and he just puts every possible thing on it, and it's this undrivable, unmanageable thing because it's got so many things. So what I'm proposing is that we will combine this Bader protocol, where you use the Hongo-Mandel dip to equalize path lengths, and then you record the detection times. And we'll combine it with these frequency-entangled photons that don't just give you a Hongo-Mandel dip, they give you these really fine fringes. And so that allows you to equalize the path lengths better than if you just use a Hongo-Mandel dip. And then we'll use this chirped pulse gating in order to convert timing into frequency, and then we'll use this quantum weak measurements to measure the frequency really well. And okay, so this is a very recent, as of yesterday, calculation. Again, not really vetted, so it could be that there's issues with it, but it seems like we might actually be able to then measure the clock offsets to within some tens of attoseconds, which maybe is interesting. Okay, looking forward to talking to people more about that afterward. Okay, so this is the end of the outline. I've kind of gone through everything. I just want to highlight there's more to be discussed on all of these things at this quantum sessions on Wednesday. And I want to thank the people. I asked some of the other speakers if they would send me slides, and they were very kind, and they did, and then I didn't include them because my timing was not quite to allow for that. So my apologies to them. But people talking about using White Rabbit to synchronize nodes and using some of these other techniques to solve the synchronization problem. So hope to see everyone there. And I started with Einstein. I will finish with Einstein. Always good to end with a quote by Einstein. So never stop questioning. I'm happy to take your questions. So with all of its pieces and all of its contraptions that are added on, oh, in fact, I left out you could do recycled weak measurements, which allow you to keep all of the photons at the end as well. Yep. So that really came into fruition about 40 hours ago. So I think before building it, you need some more careful modeling to make sure that there isn't some component that ruins some other component. But I think it's interesting, even not for clock synchronization, just seeing can you get better timing on the detectors. I don't see any reason why it wouldn't work, so I certainly think we would try to demonstrate that because I think it'd be interesting. Certainly there must be, whenever you make a detector that has a better capability, you unlock other things that you can study, even things you didn't know that people care about. Oh, I was supposed to make you talk into the speaker.
Hi. You talked about your synchronization requirement for the arrival of the photons, and it was basically you needed the synchronization the synchronization need was relative to the width of the photon. Yeah, okay. My question is, do you need the photons to actually arrive within that limit, or is it okay to just know the difference in time that they arrived?
Yeah, you absolutely, that's a great question. Unfortunately, they need to arrive. It's not enough that you know the difference because it's still, if you think, can I just quickly go back to, I want to go way back up to one of these Hongel-Mendel dips. Okay, well, that's fine. I'll just do it with my hand. So I've got the two photons coming onto the beam splitter, which is my head. Yes. The thing is, you're trying to make indistinguishable the process where both the photons go through my head and the one where both of them bounce off my head. Yes. If they come at different times, then you can tell whether or not which one was which because there's a different timing at the output. In principle, this is the thing with interference, particularly quantum interference. It has to be indistinguishable. In principle, indistinguishable. So if anyone knows, if there's a possibility of making any measurement that would distinguish which of the two things happened, that kills the interference. So it's not enough to know, they have to arrive at the same time.
So that just made me think, because all your tricks for getting around your detectors not being sensitive enough was putting in path delays. So if you knew that they were arriving at different times, could you quickly switch in a path delay to equalize them?
Sure, and I think that's actually what the Chinese group did. They did a real-time feedback based on the Hongel-Mendel dip. They did real-time feedback in order to, this one, in order to equalize the path lengths. Yep.
So then in the end, does the challenge come down to like a material science thing where you have to be able to adjust the variable path delay to get them close enough, or like what is the technical challenge that needs to be solved?
Okay, good question. So there's a couple different things. It depends a little bit on what type of, if you're in like a fiber network, where then at least things aren't moving much. They're moving with temperature drifts and things like that. So things are moving slowly enough that you can monitor that, and then that's a much easier problem. If instead you have something like a ground station and a satellite, and they're in different frames of reference, now the satellite's moving at 7 kilometers a second. I'm not going to have some delay line that's moving at 7 kilometers a second. One thing you can do in that case, if you knew exactly how fast the thing was moving, and imagine that you're sending out pulses, right? If it's coming toward you, those pulses are closer together because of the Doppler shift, and if it's moving away from you, they're further apart. And so you could, in principle, tune the repetition rate of your source to exactly compensate for that. And that would be a trick that you could use. If there's any kind of other variation, that doesn't work very well. The trick I know how to do is that you send a copy of your pump down with your photons, and so they're all going common path, and so then all of those things cancel. But that only works in certain architectures. If instead, for example, you're trying to send two photons from ground stations up to a satellite, and now they need to arrive at the same time, I don't know how to solve that problem. That's a tricky problem.
You mentioned a big difference between horizontal and vertical. Does that make a difference if you're changing your latitude or going through a twisted cable? Do you have to finesse that?
Oh, yeah. Oh, great question. Yeah, so yes, polarization gets screwed up by going through optical fiber. That's true. And it gets screwed up. Yeah, I don't have slides to show on this here, but it gets screwed up in a number of different ways, as I'm sure many of you know. But one thing, of course, is it just gets rotated to some other place. If that were it, you would just measure how the thing got rotated, and then you'd put in some wave plates, and you just rotate it back, and then you'd be done with it. That's fine, and you try to do that. The problem, of course, is that that's the thing that is drifting over time, so now I got to monitor it all the time. That's another problem. The other problem is this phenomenon that, again, many of you probably know, polarization mode dispersion, which is that if you change the wavelength, you can imagine that your fiber is, you look at the quantum state, the polarization state on the sphere after going through the fiber, and then over time it's wandering, it's doing something like this. And then you imagine taking a wavelength that's infinitesimally close to the one that you have. Instead of 1500 nanometers, it's 1500.001. And then it's more or less going to do the same thing. But if you go from 1500 to 1501, now these two are actually doing different trajectories. And if you have something that's a bandwidth that is encompassing multiple of those things, now it's kind of like mixing up your quantum state. And then you're hosed. You have to somehow fix that polarization mode dispersion. So instead of using polarization, you can use other ways of encoding, like time bin qubits, where you have an early bin and a late bin, and then it's the phase coherence between those. And then those are not usually hampered or disturbed much by fibers.
You have mentioned the experiment where you have two entangled photon sources in both sides, like the Christian's experiment. So can we use the same setup and to have a homomandel in both sides? Then, in that case, can we get at least 160 picosecond, femtosecond resolution?
I think your suggestion is do have a local delay and then a homomandel here and a local delay and have two homomandels. I have no idea. It's interesting to look at. It could be interesting. I don't know if it makes life better or not.
Okay, one more. Last question.
When you were talking about entanglement swapping and you had the two sources of entangled photons, could you just say a little bit about what those are? Because when you were talking about the entangled photons, they were coming out in a cone, which doesn't seem very efficient if you want to make an actual quantum network. So how do you generate these to be the same state?
Yeah, okay. So there's, okay, I'll give a 45-second answer. I could also give like a 3-hour answer on this. So generating, there's lots of ways to make entangled photons. These nonlinear crystals are still probably the best workhorse at the moment, but people are also looking at like quantum dots that can produce a pair of photons. If they ever get that working, that's going to put me out of business because it's going to be better in some ways. Maybe. You got to cool the things, that's a problem. We're working, and lots of other people have sources that are now on chip and in waveguides, and the two photons are coming off into single mode fibers, for example. And if you can make them slightly non-degenerate, then you can use color, wavelength to just send them to one place or another place. So there's a lot of development on this. I showed the cone picture because A, was something that I actually worked on, but B, it's like really easy to see. Oh, there's nothing super mysterious about this. Obviously, they're either born here or they're born here. It's not any kind of a super fancy thing.
Okay, well, let's thank Paul again.
Thank you, everyone.